Good afternoon again, everybody. Welcome so much to Cornell CALS and SUNY ESF's Forum on the Science Behind Forest Carbon Sequestration. I'm Julie Suarez, and I'm Associate Dean of Cornell's College of Agriculture and Life Sciences. We're here today to talk a little bit about, again, the science behind carbon sequestration and also finding natural ways to contribute to mitigating climate change. This forum is sponsored by Senator Rachel May and Assemblymember Anna Kellis. A few housekeeping rules. Again, welcome. Please enter any questions you may have in the Q&A function of the webinar. We'll be delighted to take your questions after the main presenters. And just please use that Q&A function and not the chat box. The chat can get a little bit tedious to monitor. Please know that we are now recording this session. It'll be posted online after the webinar at our Cornell CALS Forestry Extension website at Forest Connects. If you are viewing the webinar for continuing education requirements, you will receive an email after attending the webinar with further instructions from Peter Smallage, Cornell CALS Forestry Extension Associate. And again, thank you so much for joining us today. Before we get started with our speakers, we wanted to give you just a little bit of context. New York State has 30 million acres of total landmass. Of those 30 million acres, about 62% of New York State's land is actually forested. Our forested acres have been increasing since the early 1900s. You can see that graphically represented on the slide on the left-hand side of your screen, primarily as land use changed and agriculture became more efficient and marginal lands were converted to forestry uses. You can visibly see our forests by the DEC map on the right-hand side, which represents forested acres of forested parcels of 5 acres or more. It's really important to know that New York State's forests are already carbon sinks. In other words, they are sequestering more carbon than they are emitting. And again, as we think about applying what we learned today on the science behind forest carbon sequestration, we have to know who owns our forest today and why. And to develop incentives to increase forest carbon sequestration, it may help to know that 73% of our forest lands are held by private landowners. The graph on your right-hand side also shows the motivations for why people own forest land, which is also really important to understand. And people own forest land because of the beauty or the scenery, for wildlife habitat, for natural protection, for family legacies, and also, of course, for economic value of the forested lands. So now that you have a little bit of context, I'd like to turn it over today to our 2 speakers from the New York State Legislature. I'm super pleased to introduce Senator Rachel May and Assemblymember Anna Kellis. Senator May represents SUNY ESF and is also a Cornell trustee and was a lead sponsor of the CLCPA, or the Climate Leadership and Community Protection Act, in New York State when it passed. Assemblymember Kellis represents Cornell, and in our first year in office is emerging, of course, along with Senator May, as one of the leading voices for sustainability in the New York State Legislature. Both these legislators are completely knowledgeable on this topic, and I'm really glad they could provide some policy context for this forum today. Senator, I'll ask you to speak first, and then Assemblymember, if you don't mind, coming right after Senator May.
Thank you so much, Julie. And are you hearing an echo?
Yep, we can hear you.
Okay, I'm hearing an echo for some reason. I am just thrilled to be here. I'm so excited to be announced as the senator from SUNY ESF because it's really important to me. I am a 2003 graduate of the graduate program in environmental science there, and a proud Stumpy. And I'm proud to represent SUNY ESF as well. I also represent most of Syracuse and many towns in Onondaga County, all of Madison County, and a little bit of Oneida County. So I have a lot of state forest lands in my district. And 2 years and a few months ago, when we started talking about the CLCPA, my first year in the Senate, there was an announcement made that there were going to be hearings, and they said, we're going to have hearings all across the state. We're going to have one in Albany, one in New York City, and one on Long Island. And I said, wait a minute, all across the state means something different to me. And I made sure that we had a hearing at SUNY ESF and that we had forestry experts there as part of that hearing, because I was quite worried that this whole perspective was going to be left out of the conversation. And in the end, I think we ended up with quite a robust discussion as we were developing the policy in 2019 and coming out of that, since then, I think we are seeing a lot of involvement and expertise being brought to bear as that piece of legislation is implemented. So I'm excited about that. I'm thrilled to see the president of SUNY ESF on this call, as well as faculty members. And I think we'll see that the perspectives that they have are really important. We've had a lot of other legislation. One of the things about the CLCPA is it's a framework, but within that framework, we need to keep pushing the state to move in the directions that that framework envisions. And so, for example, we just passed a bill of mine to allow renewable energy installations on state reforestation lands. Oil and gas drilling is allowed on those lands now, but renewable energy is not. And that is probably less an issue about actually siting the renewables there as it is about connecting renewable energy generation across some of these state forest lands, which can create an enormous barrier to the generation and transmission of energy. So we're working from a lot of different angles, trying to make sure that the CLCPA has all the tools it needs. And I am very much looking forward to hearing the discussion today from the real experts on this, so that we can take that back and turn it into good policy in Albany. Thank you so much for having me and for doing this. And I'm looking forward to it.
Senator, thanks again. Really appreciate your remarks. And I learned something new every time I listen to you, because I didn't realize that legislation just passed. So kudos. And Assemblymember Callas?
Absolutely, and such a pleasure to be here with Senator May and co-hosting this. I'm so honored and excited. This is one of my favorite topics, as Julie knows well. I want to, for me, put this in the context of why this is so important to me, this particular topic. I have my background, obviously, being environmental studies and nutritional epidemiology. I was, particularly interested in the IPCC report that came out a while back. And one of the things that I think was the most important out of that, which is the Intergovernmental Panel on Climate Change, almost all countries in the world that got together to put that together, is that recognition that we can't just reduce our carbon consumption and reduce our emissions, that what we have put into the atmosphere right now without any further emissions is enough that could tip us over the 1.5. So we really actually need to remove simultaneously some of the carbon that we have put into the atmosphere. And we know that there's oceans, of course, being a climate or carbon sink. But as oceans get warmer, that amount that they can hold becomes less. And we have agricultural land because of the soil, and that is like the skin around the planet, that can also be an amazing carbon sink. And then the third, of course, being the forest. So this is very, very exciting because it's not straightforward. You will hear today about the fact that, as trees stop growing, they of course are not picking up as much carbon. You'll hear more about that. Also, some of the challenges that we face in protecting the trees as they're growing to maximize the carbon sequestration. So I'm very excited for all of the experts to cover a lot of that territory. And really, I sit on the assembly as a cheerleader for the scientists here who are doing the great work that I love. One of the big things that we did in the budget this year was ensure that there was a doubling of funding for the soil health research. And I'm equally interested to see what we can support in forest sequestration, afforestation initiatives. So I will certainly continue to work with all of you. I used to be a professor at Cornell myself, so this is a love of mine, both to represent Cornell, but also also to be one of the team. So thank you for that. It's my first 6 months on the legislature, so it's just the beginning. I'm excited to hear what everyone here has to share with everyone and all the techniques that we can apply. So thank you so much, everyone, for joining.
Again, Senator May and Assemblymember Kellis, I always feel that SUNY ESF and Cornell CALS are blessed to have two such stellar representatives in the state legislature for us. So thank you again for your time and for your great remarks. With that, I'm going to switch to introducing our next panelists. And we have, just a moment, my computer's stuck. We would think that we would have this technology set, but every once in a while we do seem to have a glitch. There we go. Thank you for bearing with me. So I want to introduce our fabulous trio of panelists, Dr. Tim Fahey from Cornell CALS, Dr. Julia Burton from SUNY ESF, Dr. Robert or Bob Malmsheimer from SUNY ESF, and Dr. Peter Woodbury from Cornell CALS, who will be joining us for Q&A at the end. And again, quick housekeeping, please do ask questions. Please put them into the Q&A feature. We already have a few pre-submitted ones. We're delighted to answer them at the end. Thank you. And Bob? Sorry, first up is Tim, Dr. Fahey.
Okay, so as you probably know, Cornell is naturally entirely covered with forests. And before people came on the scene, you can see the small person there on the side of that big tree. Old growth hardwood forests dominated almost all of New York State. Now, I wanted to begin by asking you to think for a moment about the woods out in back of your house, or maybe the forest down the street or up on the hillside above town, and think about where this forest came from. How did it originate? Unless you're from the Adirondacks, it's probably not an old growth forest. There are a few pockets of old growth forests left in New York. They're all basically in protected areas in nature preserves. So the forest that's out in back of your home or on the hillside is a second growth forest, or it's a forest that was cut down sometime in the past, logged over, or it grew back on agricultural land. On the next slide, I give a visual example from just south of New York. If you could advance the slides, Julie. On the right is Newfield Covered Bridge. Some of you have probably been through the Newfield Bridge, entirely surrounded by forest in 2015. And there's a photo from 1870. The bridge is over in the lower right, and there's not a tree to be seen. So the history of forest cover in New York State, as Julie showed in the next slide, was marked by nearly entirely cleared landscape at the turn of the last century. And so the forests are all dating, mostly all dating from that time. There's three types of forest. If you could advance, some were logged over and have grown back as second growth northern hardwoods for the most part. Some have grown back on agricultural fields like those above Newfield. And the next slide, naturally trees just grew back on these lands, and that's still happening in places today. And then during the Great Depression, on the next slide, the CCC crews planted extensive areas with conifer plantations. You've probably seen these out in the state forests quite a bit. All of these forests contain lots of carbon. And that's carbon that if it wasn't in the forest, it would be in the atmosphere as carbon dioxide, contributing to climate change. So we think of the carbon storage in those forests in the next slide as what we call carbon stocks. This is an example from a forest that we've studied in great detail, and shows that about equal amounts of carbon are contained in the trees, above ground, below ground biomass, and in the soil organic matter, and also some carbon in the wood that lies in dead logs on the ground. These carbon stocks are not static. In time, they change. And we call carbon sequestration the process in the next slide of the change in those carbon stocks. So if the carbon stocks are increasing through time, then the carbon sequestration rate is positive. So on the next slide is a depiction of the typical pattern of the forest carbon sequestration rate through time after a big disturbance. Like on the next slide, a microburst windstorm, for example. This happened to our research site up in New Hampshire. So on the next slide, immediately after that disturbance, the forest is actually a source of carbon. So it has a negative carbon sequestration rate. But then in time, the trees begin to dominate the equation. And over the next 100 years or so, the carbon sequestration rate accelerates and reaches a peak typically at about a century of age. Thereafter, the trees are getting older, they're growing a little bit more slowly, and the carbon sequestration rate goes down. And at about 150 years or 200 years of age, depending on the site, the carbon sequestration rate approaches zero. The forest would be carbon saturated. Now the trees are still growing. Individual trees are still growing, but their absorption of carbon dioxide from the atmosphere is matched by the emission of carbon dioxide by the decomposition of dead trees. Let me give you a typical example in the next slide from Cornell's Arnott Forest, which is down south of Ithaca. And in this slide, we're looking at carbon accumulation following the reef growth of this forest. It was pretty much entirely logged over in the late 19th century. And in 1935, Cornell foresters put in a whole bunch of permanent plots, measured thousands and thousands of trees. And we've gone back to those permanent plots periodically through time for the last 35 years. And you can see that as time goes on, the forest continues to accumulate carbon. Now we can project out into the future using a computer model. We know a lot about this forest, that the carbon will continue to accumulate for several decades, but it will approach a maximum someplace towards the end of this century. That's depicted in the next slide, the decrease in the carbon sequestration rate at that forest from 2020 out towards 2100. So the rate of sequestration will be declining in the absence of any management. Let me conclude by saying a few words about the security of those forest carbon stocks. They're always going to be at risk from natural disturbances. Forest fires are more important out west than they are in the eastern United States. Our two most important categories of disturbance are severe storms and pests and pathogens. In the next slide, I showed you this picture of a microburst. In other storms like hurricanes and tornadoes, in the next slide, a glaze storm, ice storm like we had a couple of decades ago in the Adirondacks, knocks down a lot of trees and reduces the carbon stock. In the next slide, the ones that we run into as the most important sources of disturbance today are insect pests and pathogens, including native insect pests like the forest tent caterpillar, which periodically erupts and defoliates the trees. This happened in New York State late in about 15 years ago, kills a lot of trees. The more serious problem we have now is introduced forest pests, like the hemlock woolly adelgid. So hemlock trees are dying all over New York State. And in the next slide, these sorts of dead forests are now becoming a source of carbon for quite a long period of time as those trees decay. And finally, in the next slide, others you've heard a lot about lately, emerald ash borer, which is killing all the white ash trees in New York. One of our most abundant trees, the beech tree, is affected by beech bark disease. So in summary, forest carbon and carbon sequestration rates vary a lot, but in the old forests that are pretty widespread across New York State, in the absence of management, they will not be a sink for carbon for very much longer, a few decades. However, management activities can affect that. And Julia Burton will now tell you about some of the mechanisms and approaches that are associated with that management activity.
All right. Thank you so much. Today, I'm delighted to talk with you about the role of silvicultural forest management in mitigating climate change. So silviculture refers to the practice of tending and regenerating individual forest stands for specific management objectives on a sustainable basis. So harvesting in this case is used as a tool. It is not the goal per se. And in New York, our forests provide a broad range of values and services. Not only do they provide raw materials for the many wood products that we rely on a day-to-day basis, but they provide habitat for wildlife, recreational and spiritual values. And trees can do this magical thing where they take carbon dioxide from the air and turn it into leaves, stems, and roots. And therefore, forests play a very important role in the global carbon cycle. Within individual stands, there are things that managers can do to boost the capacity of forests to mitigate climate change by sequestering carbon. However, forest management writ large must consider managing forests for climate change mitigation in the context of all these other values and services, and balance these objectives at large spatial and temporal scales. Next slide, please. So when we're talking about silvicultural management, we do need to distinguish between these carbon stocks and carbon sequestration rates. So again, carbon stocks refers to the total amount of carbon in a forest at a given time. And this can be stored in live trees, decaying wood on the forest floor, and below ground in the soil. And in managed forests, carbon is also stored off-site in the harvested wood products, whether that's short-lived products like paper or long-lived products like wood flooring. The carbon sequestration rate, again, refers to the rate of carbon uptake, for example, from the atmosphere to the trees. So, oh, I'm not done yet. So within forests, the biggest stocks are in the soil and the trees, and soil carbon can increase over long periods of time, but trees respond relatively quickly. So we need to be thinking more about stimulating carbon sequestration in the trees than the soil. However, we also need to think about protecting the soil carbon in managed forests. Okay, next slide. Next again. So carbon accumulates asymptotically in forests over time. And as Tim mentioned, these sequestration rates slow as that carbon stock begins to reach an asymptote. Silvicultural treatments can reduce stocking and reduce competition and increase resources for residual trees that can lead to increased rates of carbon sequestration among those individuals and prolong the time it takes for growth rates to decline. Next. And increase the cumulative amount of carbon sequestered over the lifespan of the trees in the stand. Next slide, or next animation. So the cumulative carbon sequestered reflects a combination of the stocks on site, as well as carbon stored in the harvested wood products, mortality, and that surplus growth we get from prolonging high growth rates of individual trees. So hundreds of years of silvicultural practice focusing on timber production and observation and research has taught us that silvicultural management can increase carbon sequestration over decades and generations of trees. So we have an app for this. Next slide. The carbon storage and sequestration capacity of a site ultimately reflects underlying characteristics like fertility and drainage, and this varies naturally across the landscape and the state. Many forests in New York are considered understocked relative to their capacity as a result of a history of high-grade logging, exploitative high-grade logging, and other disturbances, many of which, as Tim mentioned, are caused by introduced pests and pathogens. So New York's forests, by and large, are understocked. Next. Next. Furthermore, in New York, we have issues with degradation in site quality associated with the legacy of agriculture and acid rain. So in areas of the state, we have reduced the capacity to for forests to grow and sequester carbon. Next. And finally, regeneration lags associated with higher deer populations and competition with other plants like beech sprouts caused by beech bark disease can cause stands to be relatively less productive. Next. So you can see here, for example, forests in the Catskills where we've done some regeneration harvests, or my colleague has. This is in Frost Valley. On the left is an image where deer were allowed to graze and browse the vegetation. On the right is where deer have been excluded. So you can see abundant regeneration following that regeneration harvest. Next. And this is shown very clearly. This is just side by side. You can see the ferns in the understory, no trees where deer were allowed. In the background where it's fenced, you see abundant tree regeneration. Next. Okay, I'm going to kind of get in the deep end a little bit with you here. So conventional silvicultural management has a history of focusing on maximizing timber production by controlling developmental trajectories, and simplifying stand composition and structure. So this strategy aims for some narrow targets of conditions. And this is useful for maximizing timber production, but it can reduce options for the future. And given the uncertainty, there's an increasing feeling that we need to adopt a bet hedging approach that builds adaptive capacity by managing for a diversity of species and structural conditions. Next. Additionally, climate change is outpacing the ability of trees to migrate to new conditions as parts of their current ranges become unsuitable. Next. So we need another strategy beyond those we've already discussed, includes transitioning forests to species composition that's better adapted to future conditions with assisted migration. Next. And we're currently developing a long-term experimental assessment of these different climate change adaptation and mitigation strategies. Transition and restoration and rehabilitation treatments focus on building adaptive capacity relative to the conventional silviculture and no action, no management treatment. So we expect an increase in sequestration in these transition and restoration rehabilitation treatments at the expense of storage in the near term, but that this relationship may change over time as a result of that increased adaptive capacity in the face of changing environmental conditions. Next. In the grand scheme, a mix of management strategies ranging from very intensive silvicultural management to more ecologically based silviculture, and including no action and unmanaged forests will likely provide for the most benefits over space and time. On-site carbon storage will naturally increase in unmanaged forests on some lands, but may decline in others as a result of age or health-related disturbances. And silvicultural management can increase carbon storage within on-site within forests. Increase sequestration within forests and carbon storage off-site in harvested wood products. Thank you. And now I'd like to introduce our next speaker, my colleague at SUNY ESF, Dr. Bob Malmsheimer.
Good afternoon, everyone. As Julia said, I'm Bob Malmsheimer. I'm a professor of forest policy and law at ESF, where I specialize in the policy aspects of forest carbon accounting. What I'd like to do today is spend some time talking about the role that forest products and forest biomass-based energy can play in addressing climate change. Before I do that, though, I want to make clear that to address climate change, we need a landscape of mixed forests, some that are managed or not managed to maximize forest carbon stocks, others that are managed to maximize carbon sequestration, some that are managed to provide forest products and energy, and some that are managed to provide a combination of these. Next slide, please. think that we need to spend a few minutes to make sure that we all understand some basic facts. The first of which is understanding why climate change is occurring. Next slide. So I'm assuming you have all seen this figure before, but can you explain what is causing the increase in CO2 levels? Return. And as importantly, can you do so in 4 or 5 sentences? Well, let me try. For hundreds of thousands of years, CO2 levels in the Earth's atmosphere were relatively stable. However, about 200 years ago, they started increasing. Why? Because human beings started doing 2 things. Number 1, harvesting forests in an unsustainable manner. And number 2, removing what is often referred to as geologic carbon, carbon that had been locked up in the earth for hundreds of millions of years in the form of coal, oil, and natural gas, and burning it to produce energy. The use of geologic carbon released CO2 and other greenhouse gases into the atmosphere at a rate that the atmosphere could not assimilate it. It's really that simple. By understanding the basics of climate change, it's very easy to understand how to address it. We need to harvest forests sustainably and, whenever possible, not use geologic carbon to produce energy and products. So let's look at this in a little bit more depth. This graphic illustrates the problem. Notice how much CO2 emissions from coal, oil, and natural gas have increased since 1960. So this really drives home why it is so important to minimize our use of these materials to produce products and energy, which leads us directly to forests and why they are such an important part of any climate change solution. Anytime we can produce products out of wood rather than out of steel, plastic, aluminum, concrete, something like that, we are using what is called biogenic carbon, carbon that has already been circulating in the atmosphere. And remember, we're not adding any geologic carbon to the atmosphere. And it's the burning of the geologic carbon that's primarily responsible for increases in CO2 levels. As one of the co-authors on a paper I wrote put it, the carbon in trees is recycled carbon. It's already been in the atmosphere. The same is true of energy. Anytime we can produce energy from forest biomass rather than from coal, oil, or natural gas, we are producing energy with recycled carbon rather than geologic carbon, and we are providing a real, important, and permanent climate change benefit. So while most people realize that forests can sequester carbon, I want to focus the rest of my presentation on the climate change benefits of using forest-based products and energy, rather than products and energy that are produced from geologic carbon, the geologic carbon in fossil fuels. Next slide. We'll start by looking at the products that drive most timber sales, namely saw timber. Saw timber are logs that can be milled into lumber and used to produce products such as those in these photos. Next slide. To understand why forest products are a solution to climate change, we need to spend a minute dissecting this statement, which is from the peer-reviewed literature. As long as wood-producing land remains as forest, whenever we use wood products rather than products made out of steel, plastic, concrete, or other products that require high amounts of fossil fuels to manufacture, we do 2 things. Number 1, we reduce fossil fuel-based carbon emissions and get a climate change substitution benefit. And number 2, sequester additional carbon and get a climate change sequestration benefit. Next slide. The first thing we need to understand is that when we conduct life cycle assessments, we learn it takes less fossil fuel to produce wood products than to produce alternative products. This table shows us the fossil fuel energy needed to produce different products that are often used to support 1 square foot of floor. And that's what the MJ megajoules represents here. As you can see, using concrete to support a square foot of floor, uses 2.5 times more fossil fuels, more geologic carbon than using wood. And using steel to support a square foot of floor uses nearly 5 times more fossil fuels. And just to refresh our recollection, what's the problem with this? These emissions of geologic carbon are what are increasing atmospheric CO2 levels. Next slide. All of this is why there is so much interest in mass timber buildings, since they show us how using forest products provide both a sequestration and a substitution benefit. Let's start by understanding what a mass timber building is. We're talking about high-rise buildings here, 5 to 20 stories tall, that are generally used for commercial and or residential purposes. Traditionally, these buildings have been created using concrete and steel primarily. Mass timber buildings provide a sequestration benefit because the wood in them is actually sequestered carbon, since 50% of wood by mass is carbon. So when we build buildings out of wood, we are sequestering additional carbon, carbon that we would not be sequestering if we built the buildings out of steel and concrete. In addition, because we are not using as much steel and concrete, two products that produce significant fossil fuel-based carbon emissions when they are mined and manufactured, we receive a substitution benefit. Now, I want to be clear. Harvesting, transporting, and manufacturing wood does currently require the use of fossil fuels, but doing so often uses less than 10% of the fossil fuels required to mine, manufacture, and transport steel and concrete. Next slide. Here's an example of the sequestration and substitution benefits of a mass timber building on the University of Washington's campus. And in the bottom right-hand corner of the table, you can see the overall climate benefit. Next slide, please. Now, I know some of you are thinking, I understand that wood products sequester carbon in the wood product itself, but at the end of the product's useful life, the carbon from that product will be emitted into the atmosphere. So of course, some of you are thinking, Bob, that sequestration benefit is only temporary. So let's talk about that. One of two things happens when a forest product reaches the end of its useful life. If it's disposed of in a landfill, most of the wood is permanently sequestered because US laws regarding landfills create anaerobic environments in those landfills. In other words, the waterproof caps that we place under landfills and on top of landfills do not allow air into landfills. So 3/4 of the wood products in those landfills do not decay. How do we know this? The US Forest Service has actually dug up multiple landfills and measured decay. The other thing that can happen is if it's disposed in a waste to energy facility, we get a second substitution benefit because we're producing heat and or electricity without using fossil fuels, something we'll talk about in just a moment. Next slide. So now I want to talk about the role that forest biomass-based energy can play in addressing climate change, such as using wood chips in boilers to heat buildings. Next slide. Before talking about this, I think it's important to understand how much energy the US gets from bioenergy, because I don't think most people realize that 5% of US energy is from biomass. When I tell most people that biomass provides 5% of US energy, they usually say, oh, okay, it's corn-based ethanol and biodiesel. But as this slide indicates, only about 46% of US wood-based energy is currently from those products. Next slide. Most bioenergy is actually from burning wood or biomass or wood-based waste. 60% of this is used by industry. 24% of this is used in the residential and commercial sector, and 16% of this is used to produce electric power. Next slide. To understand why bioenergy is a solution to climate change, we need to spend a minute dissecting this statement, which is also based upon the peer review literature. As long as wood-producing land remains in forest, whenever we use wood-based energy rather than energy made from burning coal, natural gas, or oil, we reduce fossil fuel-based carbon emissions and get a climate change substitution benefit. Next slide. So let's look at an example of this involving heating sources often used in rural New York State. This figure shows the CO2 emissions from boilers that use fuel oil, propane, and wood pellets. I should note that because we use less energy to produce wood chips, if wood chips were added to this figure, they would have a lower total CO2 emissions than wood pellets. Notice how the total CO2 emissions from the wood pellet boiler are similar to the fuel oil boiler and more than the propane boiler. However, that's only part of the story. If we factor in that we're using biogenic carbon sourced from sustainably managed forests, we can see that the fossil fuel-based emissions are only a fraction of those using fuel oil or propane. And remember, as long as we're sustainably managing our forests, these are the emissions that we care about because they are the emissions that are causing CO2 levels in the atmosphere to rise. This is why the Germans and the Danes are working on ways to convert many of their district heating systems from fossil fuels to biomass. Next slide, please. So to end, I want to begin, I want to talk about just reiterate a statement from the IPCC regarding forests and climate change. Namely, in the long term, a sustainable forest management strategy aimed at maintaining or increasing forest carbon stocks while producing an annual sustained yield of timber, fiber, or energy from the forest will generate the largest sustained mitigation benefit. Thanks so much, and I'll hand it back to Julie now.
Excellent. Thank you so much. And I really appreciate all of our fabulous panelists and speakers. So we have quite a few questions, but right before we get to the questions, we just wanted to sum this up for you and give you a couple conclusions. The first conclusion are that New York forests provide incredible climate benefits. Policy mechanisms, whether they're economic, education and technical assistance, or environmentally based, should really be science-based to enhance forest carbon sequestration. Second conclusion, we also need to be thinking about addressing threats to our forested land and empowering our forest landowners to provide the climate benefits that we all need while stewarding biodiversity, wildlife, forest industries, and ensuring recreation and other public benefits. With that, what I'm going to do is stop sharing my screen for a moment and flip to the Q&A, so bear with me for just one moment. Our first question, which was pre-submitted, actually comes to Dr. Tim Fahey. We actually had two questions pop up involving mycorrhizal fungi, which must be very popular these days. So Tim, can you remember to unmute yourself? And if you don't mind, I'm going to combine these two questions and say, please explain how the mycorrhizal fungi content in soil, contributes to carbon sequestration, and whether or not the buildup of mycorrhizal fungi in the forest soil increases the acidity of the soil and water.
Okay, just a word about the background here. So mycorrhizae are a symbiosis between the feeder roots of the tree and certain fungi in the soil. And this is a fairly technical question, and it's really at the cutting edge of science. The first question regarding carbon accumulation in the soil is very interesting. There appear to be certain mycorrhizal fungi that promote carbon's stability in the soil. And research is identifying which fungi these are. I don't think it's likely to be a management strategy to promote these fungi, at least not in the short run. The second question had to do with the accumulation or the increase in the abundance of mycorrhizae as a forest develops. So the basic answer here is that as a forest develops, say after agricultural abandonment or logging, the forest soil is naturally acidified a little bit. And the mycorrhizae do accumulate, but the mycorrhizae themselves are not directly related to this acidification. That's a matter of mostly of the accumulation of the biomass of the trees.
Excellent, Tim, thank you so much. Now I'm going to go through these questions not in any particular sequence or sequential order. Question from one of our attendees: if a forest is clear cut, and I think this will go to either Bob or Julia, if a forest is clear cut, what happens to the carbon stored in the soil? Does it stay there as long as the soil is not disturbed?
Julia, do you
Really
want to?
my game again, I guess. Do you want me to answer it, Bob? So it's another cutting edge technical question how stable the carbon in the soil is in respect to disturbances. Most of the research suggests that only a small proportion of the carbon stored in the soil is very sensitive to the change that occurs when a forest is cut over or naturally disturbed. The dominant part of the equation of carbon sequestration rate is the trees, the growth of the trees, but there can be slight decreases in carbon stock in the soil as a result of clearing a forest. Agricultural land, on the other hand, can lose lots of carbon. If a forest is converted to agriculture and remains in agriculture for a century, you can lose half or more of the carbon that was originally in that soil.
Great, thank you, Tim. I'm not going to try and assign answers to the next couple of questions, so please pop in.
Can I follow up a little bit?
Oh, please do, Julia. Yep.
Sure. Yeah, and I would say, just kind of add to that, that in managed forests, if you're talking about a clear cut versus, a windstorm, the stability of the soil carbon seems to relate to how much of the forest floor was disturbed and whether that harvest was cut to length or whole tree harvest, for whether you're leaving some of those residues, branches, and tree biomass on site. So that can lead to some sensitivity if you're removing the forest floor, the litter layer, the organic horizon, and or the harvested tree canopies.
Great, thanks, Julia. So next question, which I think is really appropriate for our colleagues at SUNY ESF, what is the status of restoring the American chestnut tree and how good of a carbon sink will that be?
Okay, so we're working on a project looking at silvicultural strategies for restoring the transgenic American chestnut that Dr. Bill Powell developed, the Darling 58. And my thinking on this is that the chestnut is a very fast growing tree that is capable of getting very large and living a long time. So that can push that rate of sequestration up and result in a higher ceiling relative to our current species of oaks and hickories, which are also good trees. So I think if we can get chestnut back on the landscape, that does have the potential to impact to increase carbon sequestration. So faster growing trees like chestnut can make a difference. Anyone else have any thoughts on that?
Great. So again, there's another question in the Q&A from a colleague of ours, actually, at Cornell Cooperative Extension. This one may be best for Peter Woodbury. We'll see. If soil carbon is comparable to standing forest biomass, why doesn't agriculture have the same potential for carbon sequestration as forestry?
Sure, I'm glad to start on that one. As Tim mentioned, if a forest is cleared and tilled for agriculture, which is what happened in New York State, all of our tilled land once was forest, a substantial amount of carbon is lost, whether that's half, whether that's a quarter, but not all of it is lost. The potential to restore that lost carbon in agricultural soils is there. With a combination of management practices, adding more carbon to the soil and then reducing the loss from the soil, we can build up those carbon stocks in agricultural soil. Except in unusual circumstances over large areas, it would be very challenging to build up agricultural carbon stocks to equal what was in the original forest. So we can it's theoretically possible, but again, over large areas would be very challenging. So if we can only restore half or a quarter of the forest carbon soil, that's an important gain. If we took that same agricultural land and we regrew a forest, we would be increasing the soil carbon, we'd also be increasing that living tree carbon substantially, right? So there's a potential to store a great deal of carbon in the trees. So the short answer is you're getting a huge amount of carbon sequestration in a healthy forest over time in the living biomass as well as in the soil.
Excellent. Thank you, Peter. There's been a number of questions in the Q&A and in the chat that surround how do we communicate the the excellent role that forests play in sequestering carbon and that forest products play in mitigating some climate change impacts to policymakers. And I'm really pleased that Senator May and Assemblymember Kellis agreed, which is very appropriate, much more so than any of us to do so, to take a stab at answering kind of the communication question to policymakers. So I'll ask Senator May and Assemblymember Anna Kellis to join in that question, if you don't mind.
Sure, yeah, and it's fun to be on here with Anna as well, because we're kind of kindred spirits in the legislature, two women with PhDs. I taught for many years in the humanities, but it's a shock when you get into government and realize often you only have 5 or 10 minutes to get up to speed on a really big issue. And this week and next week, we're voting on hundreds of bills a day and often just do not have time. So there is a real premium on terse, brief communication, ways of summarizing an issue really carefully, really briefly for legislators, because we can't read every footnote. We do have staff, though, who are good about attending legislative briefings. If you want to do an hour like this that is aimed at legislative staff, that would be a really good thing, I think. You want to steer it away from the minutiae of the research toward what are the big picture issues, and preferably hang it on some bills that are out there to really educate people about. But another way that people get through is by writing letters of support or opposition to legislation, and we pay a lot of attention to those. So if you have an organization and you want to weigh in on a piece of legislation, write a letter, again, not a long letter, but make your key points and get them to us. That is really important. And I want to say one other thing, which is misinformation is probably more dangerous than no information at all a lot of the time. And I worry about, I put a thing in the chat about a low carbon concrete standard that we passed a bill to develop that. But I worry when you start talking about low carbon concrete, you're going to put in people's minds that, oh, there's sustainable concrete out there, we can't, the problem solved. And I do think we have to be really careful about the language we use and how we back it up.
I'll put a plug in for hempcrete.
And I will add to it just to share a story that I've shared briefly with Julia. I was having a little bit of PTSD during this session because there was the discussion that was happening was some of the data that I was trying to educate colleagues of mine when I was a county legislator, and we have county forest land, and my argument was for managing the particular part of the forest that was pine because it was at its end of its life, and everything that you heard today. And we had selected a plan for selective management of the ash in the older, not old growth, but older forests for the emerald ash borer. The science doesn't necessarily win out against poetry and romanticism. And the idea of cutting a tree in this world of climate change, there's sort of a desperate feeling like we cannot lose a single tree. I built a website, did panel discussions, wrote articles in the newspaper, trying to explain the science. Eventually I was able to get partway there. With our policy that I was putting forward at a local level, really pushing the message. The most successful message was, creating a healthy forest. what is a healthy forest, the concept of a healthy forest, because people love that word. It has a very emotional feel to it, healthy forest. And then it intrigued them, and what is going to actually, help us prevent climate change. Those things really appeal. The pictures that you saw here today, the graphs, they really do actually speak 1,000 words. So if you see that reduction in carbon sequestration as a tree gets older, that was one of my biggest selling points. And at the state level, one of the things that we can do is hold briefings and hearings during the summer to set the stage for when we come back in January, because we have more downtime during that time. So if you want to speak to a legislator, you want to educate a legislator, set up a meeting with them during those down months and prep them, build a relationship. And then by the time, you introduce a template bill to them and say, would you consider carrying this, or would you consider writing a bill on this topic? You have prepped them and primed them, and they understand what you're talking about. So that is the strategy that I would recommend, because once we hit January, at least at the state level, I can tell you it is a fast and furious sprint between January and April 1st for the budget. And then we have 2 months to pass 9,000 bills. I wish I was exaggerating, of which we only actually successfully probably pass 1,000. So, gives you a sense of, it does take time and investment, but it is possible.
Thank you again, Senator and Assembly Member. Now you can all go home with another piece of trivia. Apparently, there are almost over 14,000 legislative bills introduced in the New York State Legislature this year, which is quite a lot for any one person to handle. So I think we have time for one more question, and the questions have been coming fast and furious, and a lot of them are quite complex. I'm going to sum up and ask, I think everybody can contribute to this. How would you maximize a forest? Presumably, how would you maximize management of a forest for carbon sequestration? Don't all of our scientists answer at once?
Well, as Julia pointed out, and I think the point was, we tried to make the point that every forest is different. And so the prescription for managing every forest has to be specific to that forest's history and site quality, and also, of course, the wishes of the landowner that manages that forest.
Well,
I think
I'm a
Julia may
general-
have some other comments.
Sorry, Tim. I'll chime in and say the way to maximize carbon sequestration in forests is to have healthy, rapidly growing forests. And the techniques that it takes to get there are going to vary from site to site, but that's the goal. You need a healthy, fast-growing forest to sequester carbon.
That is an excellent way to sum up this entire session. And I want to thank again, Senator May, Assemblymember Kellis. I want to thank Tim, Bob, Julia, and Peter for joining us today. I also received a few questions about in the chat of, can we get copies of the slides? So as a registered attendee, I will be more than happy to email you after this, probably next week, with copies of the slides. And don't forget that the recorded presentation will be available on our Cornell CALS Forest Connects website, which you can just do a quick and easy Google search, Cornell Forest Connects, and that will pop right up. Really appreciate your time and attention today, and I thought this forum was fabulous. And thank you so much for joining us on a Friday afternoon when the sun is shining, at least where I am. And I hope you all enjoy your weekend. Thank you again.
Thank you.
Bye, everybody.
Everyone.
Take care, everyone.